In this video, I will show you an AC circuit example using superposition theorem. In a circuit, we apply superposition theorem when the circuit contains more than one energy source. Therefore, we keep one source active. We keep one source active at a time. Now see, in this circuit, we have to calculate the current through the capacitor of minus J5, capacitive reactance of minus J5 using superposition theorem. See, in this circuit we have this 100 phase angle 0 degree voltage source, this 10 phase angle 30 degree ampere current source, and we have to calculate the current through this minus J5 ohm capacitive reactance. Okay, as we have to calculate the current through this capacitive reactance. First, I will keep this 100 phase angle 0 degree voltage source active. In that case, the current that will be flowing through this minus J5 capacitive reactance IC1. After that, I will keep this 10 phase angle 30 degree current source active. In that case, let's say the current will be flowing through this capacitive reactance IC2. If they are flowing in the same direction, I will simply add them up. Or if they are flowing in the opposite direction, I will take the subtraction of them to get the current flow through this capacitive reactance. Okay, so here at first I will keep this 100 phase angle 0 degree voltage source active. When I will keep any source active, if there are any other current sources or current source in a circuit, that will be replaced by open circuit, and if there are any other voltage source in the circuit, that voltage source will be replaced by a short circuit. So here I will keep this 100 phase angle 0 degree volt active. In that case, this current source will be replaced by open circuit, and see, our new circuit will look like this. Okay, see, I have replaced the current source with an open circuit. That means there will be no current flow. When I will keep this voltage source active, there will be no current flow through this path. Okay, now see, this is our voltage source. Here, let's say at first this source will supply a current I in the circuit. That current I will be same up to this point. Here it will divide into two portions. One will go in this direction, another will go in this direction. Let's say the current that will be flowing through this path will be IC1, and that will be flowing in this direction. Okay, see, if this is positive terminal, this is negative terminal during positive half cycle. So IC1 will be flowing in this direction, and let's say the current that will be flowing through this path is I1. So this I1 will be same up to this point. I1 and IC1 will combine and return to the source as total current I. So this will be the total current flow in the circuit. Now see, from this point to this point in this branch, we have this 3 ohm resistance and the inductive reactance of J4. Therefore, in this branch our impedance will be, let's say, Z2. Here Z2 will be equal to 3 plus J4 ohm. Okay, and from this point to this point through this path, we have this impedance of 5 minus J5. Let's say I denote that impedance with Z3. Here Z3 will be equal to 5 minus J5 ohm. Now see, with respect to those two terminals, Z2 and Z3 will be parallel. Let's say their equivalent parallel in impedance will be equal to Z equivalent, Z2 parallel Z3. When we have two impedances connected in parallel, we calculate their equivalent impedance by using this formula, Z2 into Z3 divided by Z2 plus Z3. Now see, if I reduce Z2 and Z3 to a single impedance of Z equivalent, that Z equivalent will be in series with this 5 ohm resistor. Therefore, the total impedance of this circuit with respect to the two terminals in which our source is connected, ZT, will be equal to 5 ohm, that will be in series with the Z equivalent, and Z equivalent is the equivalent impedance of Z2 parallel Z3, so it will be Z2 into Z3 divided by Z2 plus Z3. Here it will be equal to 5 plus 3 plus J4 into 5 minus J5 divided by 3 plus J4 plus 5 minus J5. This will be equal to 5 plus 4.23 plus J 1.15. So the total impedance with respect to the two terminals in which our source is connected will be 9.23 plus J 1.15. So if I take the polar form of 9.23 plus J 1.15, there I will get total impedance ZT equal to 9.30 phase angle 7.12 degree. Phase angle will be 7.12 degree. Now see, in this circuit we know the value of total impedance ZT. We know the value of total supply voltage. Okay, so if we want to calculate the total current in the circuit, total current is I. How do we calculate total current? We divide total voltage with the total impedance of the circuit. Total impedance is 9.30 phase angle 7.12 degree, and that will be equal to 10.75 with phase angle minus 7.13 degree. Okay, so this is our total current in the circuit. Now see, we will calculate IC1 that is flowing through the impedance Z3. See here, we have two branches connected in parallel. One contains impedance of Z2, another contains impedance of Z3. So when we have two impedances connected in parallel, we simply use special current divider rule to calculate the current in that branch. Here I will calculate IC1 that is flowing through the impedance of Z3. Therefore, if I want to calculate the current through this branch with impedance Z3, I will take the impedance of opposite branch Z2 divided by the sum of two impedances Z2 plus Z3 into total current I. Z2 is equal to 3 plus J4. Z3 is equal to 5 minus J5, and I will multiply this with 10.75. Phase angle will be minus 7.13 degree. Therefore, IC1 will be flowing from left to right, and the value of IC1 will be equal to 6.67. Phase angle will be 53.15 degree. And finally, I will keep this current source active. I will keep this 10 phase angle 30 degree ampere current source active. In that case, I will replace this voltage source with a short circuit. When I will replace this voltage source with a short circuit, you will see our new circuit will look like this. Okay, so this is our circuit. See, I have replaced the voltage source with a short circuit. Now see, this is our current source. It will supply current source up to this point. The current will remain same up to this point. Here it will divide. One will go in this direction, another portion will go in this direction. This portion will further divide. One will go in this direction, another will go in this direction. See, we have to calculate the current through this minus J5 ohm. Therefore, for this current source, let's say I denote that current with IC2. See, I can easily apply special current divider rule to calculate IC2 if I replace these two impedances with a single impedance as they are connected in parallel. Okay, let's say I denote that their equivalent impedance with Z5. See here, from this point to this point I have this Z3. Z3 will be equal to 5 ohm only, and from this point to this point, this branch impedance I denote that with Z4. Z3 will be equal to 5 ohm. Z4 will be equal to 3 plus J4, and they will be connected in parallel. Therefore, I can replace them with a single impedance, and their equivalent impedance will be Z5. Z5 will be equivalent impedance of Z3 in parallel with Z4. So I will use this formula: Z3 into Z4 divided by Z3 plus Z4, which will be equal to 5 into 3 plus J4, 5 plus 3 plus J4. This will be equal to 2.5 plus J 1.25. This indicates that Z5 will have a resistive value of 2.5 and inductive reactance of 1.25. So our new circuit will look like this. See, this is our Z5. See, this is the resistive portion of Z5. This is the inductive portion of Z5. Okay, now see, look at this terminal and this terminal. I have this current source supplying current at this point. Here it will divide into two portions. One will go in this direction, another will go in this direction. The current in this portion is IC2. Let's say from this point to this point along this branch, the total impedance is Z6. So what will be the value of Z6? You will see Z6 will be 2.5 plus J 1.25 minus J5. So here I will get 2.5 minus J 3.75, this ohm. Okay, and this branch will have an impedance of, let's say, Z7. Z7 will be equal to 5 plus J0. Okay, now see, I have to calculate IC2 as I have to calculate the current through this branch. I will use special current divider rule. While calculating IC2 through this branch, I will take the impedance of opposite branch Z7 divided by Z6 plus Z7. Z7 divided by Z6 plus Z7. Multiply this with current. Here current is 10 phase angle 30 degree. Z7 is only 5 and Z6 is equal to 2.5 minus J 3.75 into 10 phase angle 30 degree. So IC2 will be flowing from right to left, and it will be equal to 5.96 with phase angle 56.57 degree. So here in the circuit, IC1 was flowing from left to right, and IC2 is flowing from right to left, and the value of IC1 was greater than IC2. So if I subtract IC2 from IC1, I will get our current through the minus J5 ohm capacitive reactance. IC will be equal to 6.67 phase angle 53.15 degree minus 5.96 phase angle 56.57 degree. So the current will be equal to 0.80 with phase angle 26.89 degree ampere. So this will be the current that is flowing through the capacitive reactance of minus J5 ohm. Okay, that's it. Thank you.